Good morning, friends. In last lecture, we have been seen what is the dropwise condensation and filmwise condensation. Now, moving towards the coefficient for film type condensation. I told you, if you do remember, practically formation of droplets on the outer side of the condenser is tube is not possible at all. So, by assuming that there is a film-wise condensation, it is always to better assume such a conditions for design. So, while designing any equation, we are using or we are assuming that a dropwise condensation is taking place inside the heat exchange equipment. Now, I told you one more thing, that heat exchange equipment can be kept vertically or horizontally also with respect to the space available inside the plant. So, here how the heat transfer coefficient is inversely proportional to the thickness of the condensate on the vertical tube we are going to discuss. So, as shown in diagram, figure number 13.1, there is a one plot which has been drawn against film thickness against distance from top of tube. So generally, when the condensation takes place, that time uh, condensate is going to accumulate at the top of the tube, and slowly the thickness of the condensate is getting changed, that is reduced from top to bottom. And that is why the heat transfer coefficient is inversely proportional to the ratio of thermal conductivity of the fluid layer or condensate layer as well as the film thickness. So mathematically we may say Hx is equal to Kf upon del, where Hx is nothing but individual heat transfer coefficient, and our film coefficient we can say, and Kf is nothing but thermal conductivity of the that fluid layer or film layer, sorry. So Kf is also called as fluid or film because the condensate is nothing but the fluid, that is liquid. So Hs is equal to Kf upon del, where Kf is nothing but thermal conductivity of the film and del is nothing but film thickness. So generally heat transfer coefficient is inversely proportional with the film thickness. Now moving towards the diagram, as shown in 13.1, this diagram is drawn for the film thickness and the local coefficients depending upon the film of condensate. So if you will see, at the beginning the heat transfer coefficient, there are two lines which are drawn which are intercepting. One line is showing heat transfer coefficient and another line is showing film thickness. So as film thickness is going to increase, the heat transfer coefficient is going to decrease, and vice versa. As film thickness is going to decrease, the heat transfer rate is going to increase. So very simply, by plotting this graph, we can correlate the relationship in between film thickness and distance from the top of the tube. So that condensate loading is nothing but amount of droplet or condensate which is formed on the tube, outside the tube. Generally, a cold commodity is passed through the tube side, and the mixture or vapors are allowed to enter into the shell side. So whenever a mixture of vapors are getting a temperature which is less than condensation temperature, then at that temperature the phase transfer takes place, that is the vapors are going to condense on the outer wall of the tube, and thus heat of condensation we have been discussed earlier, and heat of vaporization, both are that important. Here heat of condensation is very important. Unless and until that vapors are not giving their heat, they cannot get condensed, and undoubtedly the fluid which is used as a commodity to condensate that vapors, they will get warm the temperature of the cold water will get increased, or cold commodity will increased, and thus the condensate will get form in our liquid form, condensate, that is the condensation of vapors. Now, as per the thickness of concern, del is equal to 3 tau, the tau is nothing but condensate loading, mu f, that is the viscosity of the film, upon density square, that is rho square g, and the it entire value raised to 1 by 3. This is the condensate loading. So we have been seen one equation, that is hx is equal to kf upon del, uh, and here we are seeing del is equal to 3 dou mu f upon uh, rho square g raised to 1 upon 3. Now, by replacing this dou term into above equation, hx is equal to kf upon dou, we may get this equation, hx is equal to kf into bracket rho square g upon 3 tau mu f upon raised to 1 upon 3. This is just mathematical adjustment, being the value at the denominator again becoming to coming to the numerator, and this just simply we are getting equation number 13.3. This equation is applied to condensation either inside or outside of the tube. So once again I will repeat the equation, hx, that is heat transfer coefficient, is equal to kf, that is the thermal conductivity of the film, into bracket rho square g upon 3 tau mu f raised to 1 upon 3, where needless to mention, rho is the density, g is the acceleration due to gravity, tau is the condensate loading, and mu is nothing but viscosity of the film. So undoubtedly viscosity of fluid plays a very important role. If it is sticky, again the rate of heat transfer will be different. If it will have the less viscosity, again the value will be different. So for vertical tubes, the local coefficient can be correlated by the relation hx is equal to dq upon del t dA naught, that is outside del TO, outside temperature gradient, and the dA naught is nothing but outside area of the tube. Here you must notice one thing, that we are interested in outer part of the condensate tube, or tube side, outer part of the tube side, that is shell side. So hx is again we can correlate by lambda dm bar upon delta TO, that is outer heat transfer gradient or heat temperature gradient, pi do dl, where lambda is nothing but heat of vaporization. I told you, heat of vaporization and heat of condensation recently we have been discussed. M dot is nothing but local flow rate of the, or mass flow rate of the condensate. Now this equation may be written as hx is equal to lambda d tau upon delta TO dl, and the average heat transfer coefficient for entire tube can be defined by h is equal to qt upon AO upon delta TO is equal to m dot t lambda upon pi do LT delta TO delta T outside, that is the temperature gradient at the outside, is equal to lambda b into tau upon LT delta TO, where QT is nothing but total rate of heat transfer, m dot tau is nothing but total rate of condensation or that layer, LT is nothing but total length of the tube, and tau B is nothing but condensate loading at bottom of tube. So simply you should understand that the condensate layer is going to decrease, the thickness is going to decrease from top to bottom. At the bottom, with respect to height, the amount of condensate might be very less. So this is all about the average heat transfer coefficient. Here the equations have been elaborated with respect to conditions like vertical as well as the horizontal. Now we will discuss horizontal for the heat transfer coefficient at a horizontal tube in another lecture. Thank you.